We're going to start first with somebody who's particularly special to us. Mr. Chris Scolese is a graduate of Buffalo, or UB, and he currently serves as the director of Goddard Space Flight Center. He previously served as acting NASA administrator in 2009, and he is current head of one of our nation's most critical robotic research facilities. So we welcome Mr. Chris Scolese.
Well, good morning, everybody. I see we're starting kind of early, so we're going to have to filter some people in. How many students are here, since I see a number of ties? Okay, so students are just probably rolling out of bed anyway. Well, thanks for inviting me here. It's great to be back in Buffalo. As was mentioned, I grew up here, not very far from downtown Buffalo. We have another Buffalo native as well here. We'll be talking to you today. To let you know, I graduated from the University of Buffalo in 1978, and started my career in the Navy, and eventually ended up at NASA, where I really always wanted to be, doing some great things as you heard about. But just to let you know, for any of you who are from the University of Buffalo, we have 12 other graduates of the University of Buffalo at Goddard, and we have several at the within NASA. So let me get started and start talking about Goddard. Let's see. Did it change up there? No. Let's try again. Doesn't seem to be working. There we go. Okay. Talk a little bit about Goddard. It was the first center started by NASA. Now, many of you who know the history of the space program know that there was a JPL before there was a Goddard, and there was a Marshall before there was a Goddard. But those were under different organizations, and there was a Langley before there was a Goddard. It was NACA. But after they formed NASA, they started with, my screen up here keeps on flickering, which has me a little bit confused. Sorry about that. They created Goddard Space Flight Center in 1959. And the purpose of Goddard is really to go off and do the exploration of the universe and our Earth. We have the largest collection of scientists and engineers in the U.S. In the old days, it used to be Bell Labs, but with Bell Labs going away, we took the #1 spot. We've had about 300 successful missions throughout the life of the Goddard Space Flight Center, and we continue to do more and more missions. Some of the highlights of our missions is we did the first weather satellite, and we continue to do weather satellites. The Hubble Space Telescope, mostly the repair missions, and that went on, and many more. We have the 2006 Nobel Prize in Physics. One of the people that shared that prize, John Mather, is at Goddard Space Flight Center, and they got it for a satellite that was actually built at the Goddard Space Flight Center called the Cosmic Background Explorer, or COBE. Hubble has supported at least 2 Nobel Prizes with the results from Hubble, most recently in 2011. And we continue to move on with science missions with WMAP, getting a distinguished award. Oops, that's gone the wrong way. There we go. This gives you the sense of some of the 300 missions that we did, and what you can see with all the missions, and they're sort of organized by where they are. There's several around the Earth. They're looking at the Earth or looking out at the cosmos. There's some around the sun or focused on the sun, and there's several that have gone to the planets. Although in the case of the planets, I have to say that what Goddard does is mostly build the instruments that go to the planets. And as of today, Goddard Space Flight Center has has built more of the instruments that have flown to the planets than any other organization in the world. We fly on JPL spacecraft, we fly on international spacecrafts from ESA and Japan and other nations. We do have a few planetary missions or interplanetary missions that we do. I'll talk about two of those coming up in a little bit. Now, one thing I do have to point out is we don't consider the moon another planet, so we've had many missions going to the moon as well. As you can see, the missions span everything that you would think for a science center. We do the astrophysics, as I mentioned. That's looking at the fundamental structure and fabric of the universe and to understand our place in it. Heliophysics, to understand the sun and its interaction with the Earth. Planetary and lunar, to understand our nearest neighbors. Earth science, to understand our Earth, and I'll talk more about each of these. Cross-cutting technologies, communications, and the suborbital programs. I'll spend a bit of time on those. I mentioned the moon, and we have a satellite LRO that was built at the Goddard Space Flight Center, launched several years ago. It's orbiting the moon. It has some interesting instruments. This is showing the topography of the moon. It's a laser instrument that was developed, designed, and built at Goddard Space Flight Center. And combining it with imagery, we're able to get the relief of the moon and provide us much better indications of where to land when we send humans or robotic spacecraft to the moon. It also proved without a doubt that we landed on the moon. So those people that say we didn't, there's the Apollo 17 landing site. And you can see some interesting things. You can see the lander, you can see the rover, but more importantly, you can see the tracks that are there. I had the opportunity to sit down and talk with Jack Schmidt, who was on Apollo 17. And he gave a splendid lecture that if you ever get a chance to hear it, you should really go and hear it, particularly if you're a geologist. I'm an electrical engineer, so I appreciated it, but I probably couldn't appreciate it as well as a geologist. And what he did was Apollo 17, Taurus Littrow, 40 years later. And you might say, well, gee whiz, he didn't go back there. Obviously, no one's gone back there since Apollo 17. But with the data from LRO, he was able to do a walkthrough of where they went on the moon during Apollo 17, what they learned while they were there from the rocks they brought back, and how the data now that we can get remotely from our spacecraft has changed their understanding or confirmed their understanding of what they learned about the moon from Apollo 17 and actually all of the Apollo missions. So it was just a spectacular lecture. I think it was videotaped. I think you can probably find it on YouTube at some point. And it was about an hour, and it's well worth listening to if you want to hear stories about what it was like to live and work on the moon, but more importantly, what we learned and what we're continuing to learn. I don't want to do that again. There we go. We also are looking at the sun, as I mentioned earlier. It's the nearest star to the Earth. Obviously, it's life-sustaining for us, but it's also creating nuisances as we become much more technological. Our infrastructure is impacted by the sun, the electrical power grid. Many of you probably know that in Montreal several years ago, a solar flare interrupted the power and caused a power outage there. It affects our communication satellites around the Earth. So understanding the sun is something absolutely critical for us to do. The images you saw here came from the Solar Dynamics Observatory, another satellite that was built at the Goddard Space Flight Center. But in this case, the study of the sun is truly an international effort. And we work with many nations and other organizations within the U.S. government to look at the sun, monitor the sun, and to develop a predictive capability as to when we're going to have solar flares and what direction they're going to go in, so that we can much better protect our infrastructure. Let's see. Let's try that. Got a new one. Let's see. Nope, I'll stick with this one. Let's see. Okay. I mentioned astronomy, and the Hubble Space Telescope is something I'm sure you're well aware of. This is an animation of the deep field that was taken by the Hubble Space Telescope. The interesting thing about this deep field is the deepest field that's ever been taken, and this is just a segment of it that was taken by combining images that had been taken over the years by Hubble and combining them so that you could pull out the signal to get the deepest field. This is an example of data that comes from a small Explorer satellite that was done by scientists at the Goddard Space Flight Center and Penn State, with instruments that were developed at Penn State and Goddard Space Flight Center. And what that showed was the accretion of a black hole, what happens around the black hole. And that data came from the SWIFT mission that gave us new understanding of how to do and understand black holes. Okay. Is there a new image up there? Earth science satellites that I mentioned earlier. This is just an animation of all the Earth science satellites that we have orbiting the Earth. And then the focus areas that we look at, the atmosphere, the oceans, the Earth, the bioproductivity of the Earth that you're seeing in some of these images, temperatures, so that we can go off and provide the policymakers better information on where to grow crops. So that's information to the farmers and the policymakers, where to place infrastructure. You don't want to build a dam today and find out that the river isn't going to be there in 100 years. You want to build a dam where it's going to produce over the expected life of a dam, which is 100 years or more. So our Earth science data is directly applicable to what we do every day. Oops. Now let me talk, a little bit about, where we are today and where we're going to go in the future. The name of this conference is Crossroads, and it's an important name. I don't know how you all came up with it, but it's a very apropos name for this time period that we're at, because we really are at crossroads as we go off and start expanding our knowledge using robotic spacecraft and start moving in a new and different direction with human spaceflight. And they're merging more and more together. They've always sort of been there. If you think about Apollo and what we did on Apollo, before any astronaut landed on the moon, of course we looked at it with telescopes, but we also looked at it with orbiting spacecraft, the Rangers and the lunar orbiters. We landed on the moon with surveyors. The Russians were doing the same thing. And eventually, we had humans on the surface of the moon. Our technological capabilities at the time weren't such that we could do as much with robotic spacecraft. But we just recently landed on Mars with Curiosity. When we sent humans to the moon long ago, and before some of you students were born, certainly, we sent them out of the protective cocoon of the Earth's magnetic field. So any solar eruption could be fatal to a crew that was in space. Without having the knowledge of the sun that one needed, they had solar observatories all around the world and solar physicists staring at the sun all during the missions, before the missions, during the missions, and shortly thereafter. to look at the sun and try and determine if something was going to happen. So prior to the mission, they might have delayed a mission. They never did for a solar influence. During the missions, they were to tell the crew, don't land, come home, if they saw a solar flare. And when you're only 2 or 3 days away from Earth, that's something that one can think about. We came close. On Apollo 15, there was a solar flare shortly after the crew landed, and it was determined that had it happened during the mission, it probably would have been fatal to the crew. So now we have a bunch of solar sentinels that are coming from all around the agency. This is the latest blue marble, if you will. For those of us who are old enough to remember Apollo 8, the first time we saw this, it really changed the view of the world towards our Earth, and many credit it with starting the environmental movement. Well, now we can do this on a daily basis. What's the importance of it? Well, just think of Hurricane Sandy. Without the daily monitoring of the Earth's environment, as a minimum, we wouldn't know when severe storms were coming, where they were going to go, and what their likely impact was going to be. There's another benefit of it. If you kind of know where it's going to go and you know what the impact is going to be, you evacuate a minimum amount of people, you disrupt the lives of a minimum number of people, and you in place infrastructure where it needs to be to help as best one can when the storm or the natural disaster, whatever it might be, hits. Because we can't stop a hurricane yet. Maybe somebody in the audience here will figure out a way to do that. But today we can't do that. So we have to be able to mitigate it. And the other thing is, we help travelers. Those of us who fly a lot know that when you get stuck in Chicago or Buffalo or Boston because of the storm, sometimes you can't get a hotel room, so you sleep in the airport, which isn't very much fun. Or you can't get work done, or you can't get goods to the right place. So with adequate knowledge, we can, adjust our travel plans. We can make sure aircraft are not, in the wrong place. We can hold up trains or put them on different routes, or reroute trucks to different areas so that we maintain our level of commerce. Landsat is an interesting mission. It started 40 years ago in 1972 when the first satellite was launched. And as of today, it's the longest continuous data record that we have of the Earth. I mentioned the weather satellites. Well, in 1961, when we launched the first weather satellite, it took really grainy, I don't have the image here, black and white images in the infrared that showed that clouds do indeed exist. But it didn't show much more. So that record didn't really start getting better until 1978. But in 1972, because of experiments conducted on Gemini and Apollo, we knew that there was a lot more data out there that we could get from space that would tell us about some of the things I mentioned earlier: agriculture, land use, flooding, what have you. So Landsat's been going for 40 years, and we continue. We have a new mission that should launch early next year to continue that data set. Sounding rockets. Many people think that sounding rockets have gone away, but sounding rockets are really critical. At Goddard, we have a facility called the Wallops Flight Facility. It's located on the eastern shore of Virginia, and we do sounding rocket and balloon payloads from there. If you recall the chart I showed earlier, I showed sounding rockets way off on the right. What we do with sounding rockets is fundamental science, fundamental research. They also serve as a place where scientists and engineers can do experiments quickly, so they end up being training grounds. A sounding rocket or balloon experiment can be conceived, developed, designed, built, tested, flown, and data reduced in 3 years. So if you're a PhD student, I don't know if there's any PhD students out there, you can get your dissertation done. If you're a scientist, you can go off and verify a theory or a component earlier in the process than you would with a space mission, and therefore be ready with a space mission. Last year we launched, I've got to look it up here, we launched 5 suborbital rockets within 80 seconds. And that white cloud you see there is a release, a chemical release from the sounding rockets, so that we can see how upper atmosphere winds interact. The reason I show this is because the event was something that could be seen as far south as North Carolina, but we understand from people at the University of Buffalo and at Canisius that it was seen up here in Buffalo as well. So we know it was seen as far north as Buffalo. So that's something that was pretty good. Unfortunately, me, who lives only 100 miles from there, couldn't see it because there were clouds. So I didn't get to see it. What this is not a UFO. That's Venus. And the day of the Venus transit of the sun is something that's remarkable in our lifetimes, because it happens in pairs every 105 or 121 years. This is the second pair, the second one of the pair for this time. The next Venus transit will be in 2117, so a bit of ways away. The reason that this is interesting is the first time we were able to look at a Venus transit from space and to collect the data. So the data is still being looked at to understand what it means. It'll help us with everything from understanding Venus and understanding the sun to being able to improve our clocks. So, and you can see this image and other images. This again came from SDO. The other reason it's important is, for many of us, the sky was cloudy on that transit. You couldn't see it if you wanted to. I don't know what it was like up here in Buffalo, but down in the Washington area, it was very cloudy, so we had no way to see it. So I watched it on a monitor and saw it, because our space assets could go off and look at it for us. This shows some of the other measurements that we get from space. Arctic sea ice is something that's been decreasing. Interestingly, as the Arctic sea ice is decreasing, the Antarctic ice is increasing. It's something that the scientists have to figure out. We've had the greatest loss of Arctic sea ice that's been recorded, at least in the space age. And as you can see in this image, there's now a Northwest Passage that has been looked for. So people are starting to take advantage of that with the data, and it also adds to some concerns that we have about our Earth's climate. Recently, we launched the Radiation Storm Probes mission with our colleagues at the Advanced Physics Lab. Lots of instruments on there. It's a pair of spacecraft to understand the interaction of the sun with the Earth's magnetic field, and it's in the Van Allen belts. It's something we haven't really done since the beginning of the space age, when Explorer 1 was launched, excuse me, in 1958. LRO, I mentioned it earlier. The interesting thing about LRO is it's still finding new data that we didn't know about, from Apollo. People think that we've learned a lot, and we learned all we needed to learn about the moon from Apollo. That's anything from the case. Again, if you can hear Jack Schmidt's lecture, that would be great to hear how 40 years later we're still learning about the moon. The other thing that we did, which was sort of a PR type of a thing, is we imaged all of the Apollo landing sites. And if you ever get into a trivia match, you can definitively say that 6 of the flags are still standing. The 7th from Apollo 11 is not. And those of you who listened to the Apollo 11 audio, you'll hear Buzz Aldrin saying that as they launched, that he believed the flag had fallen over when by the overpressure from the liftoff, and in fact we confirmed that. And what you can see here in the very highest resolution image in the image there again of Apollo 17, you can see the flag and you can see the shadow of the flag at that particular time. Now let's talk about other things that we're doing that are going to open up our pathways for the future. Because many people have said that, with the end of the shuttle program, that we really weren't doing anything in space anymore. Well, it's the farthest thing from the truth. This is just an indication of stuff we have done that and launched. And now I'll talk about some of the stuff that is either recently arrived, like Curiosity on Mars, and what we're thinking about for the future. Curiosity carries an experiment called SAM, Sample Analysis at Mars. And you'll discover we are very clever with our naming. But what SAM is a chemistry lab that's more powerful than what they had during the 1960s and 70s for Apollo when they examined the moon rocks that came back from the moon. That's now sitting on the surface of Mars. To date, we've sampled the atmosphere and made some very interesting results, really changing our understanding of the Martian atmosphere. Most of our data on the Martian atmosphere that was measured directly comes from Viking that landed in 1976. We now have much better understanding of the isotopic ratios on Mars, and it's changing, as I said, the understanding of the atmosphere already. One of the recent results is that the amount of methane that Viking did not see methane. Orbital assets have said that they see seasonal variations of methane, and they believe high concentrations of methane. We know we're in the low season, and it's much lower than people expected. What that means yet, we don't know. We're going to have to wait a Martian year to figure out if that's a relevant result or not. It's also starting to take solid samples. And solid samples are something we have to be careful of. We can take 80 solid samples and that's it. So over a 2-year mission, the scientists are going to want to carefully pick those 80 samples. What we're doing now is running solid samples through it to make sure that there's no earth, dirt, dust really in there, and that we're only looking at Mars. Where that first sample is going to be, I don't really know. The scientists haven't picked that yet, but expect results very soon about the chemical composition of the Martian soil. Again, something that has not been done since Viking, with very limited instruments by comparison to SAM. So for those scientists of you, they're still analyzing the Viking data. And that's 30, 40 years later. So I expect that we'll be analyzing the Curiosity data 30 and 40 years from now as well. So lots and lots of data will be coming back, and it'll be a much longer mission over a broader area. This is something that's interesting. This is a pure science result that came from our scientists at Goddard, looking at meteorites that have come down on the Earth. They have determined that the building blocks of our DNA, the nucleotides, actually can be formed in space. They're continuing that research and will be looking to expand on it, both from an astrobiology standpoint, which combines what we know about biology on the Earth, which has expanded recently over the last decades, as we've discovered extremophiles at the bottom of the ocean, to look at more exotic life forms. So they're going to be looking at that not only through meteorites and research where they run experiments, but also as with other missions. OSIRIS-REx is another mission. This is one of the first true planetary missions that the Goddard Space Flight Center is developing, and it's a really challenging mission. This mission will fly out to an asteroid. It will put out an arm, a puff of nitrogen, and mix up the regolith and bring back a sample to Earth of the regolith. We're hoping to bring back at least 60 grams of an asteroid. The first time we're going to actually bring back a sample from an asteroid. Now we brought back samples from cometary dust, from the tail of a comet, and of the solar wind recently. This will be an actual sample from the surface of an asteroid. Part of the reason for that is to go off and see if in fact the building blocks of life do exist out in space. We're getting the meteorites. We roughly know where the meteorites come from, whether they come from Mars or they come from an asteroid. The one I showed you happened to have come from an asteroid. So, we'll get some direct measurements where it hasn't been burned up by the Earth's atmosphere and hasn't stayed on the Earth, and confirm whether or not we are seeing the building blocks of life. And just to show you how torturous it is to come up with a cool name like OSIRIS-REx, what it really stands for is Origins, Spectral Interpretation, Resource Identification, Security Regolith Explorer. Now tell me that isn't, that's why people get PhDs, so they can come up with all those fancy names. JWST, it's going to be, the largest telescope to fly in space. And it's going to be the most complicated telescope to fly in space, and probably one of the most complicated things that we've ever flown in space, perhaps, rivaling the space station. But if not, I would say it's a close second. When you think about JWST, you have to completely change your understanding of things. The mirror that's there is 6.5 meters in diameter. It's made up of 18 segments. The backside, if you will, of this telescope, which I don't, let's see, the backside of this telescope, this side of it, is at about 300 Kelvin. This side of it is at about 30 Kelvin. So we have about a 250 Kelvin difference in temperature between the two sides of it. The shield to do it is the size of a tennis court. There's 5 independent shields, the size of a tennis court, and the thickness of a space blanket that you can buy from Target for $1. That's required us to have a totally different understanding of our physics of glues, bonding agents, because the thermal stresses are worse than any of the mechanical stresses that you have from launch, which usually is the biggest thing that we have to worry about. Once we cool it down, we never want to warm it up again for fear of what's going to happen. But to add to the complexity, there's 18 mirror segments in here. In order to focus it on what you want to focus it on, we have motors behind each one of those to deform those mirrors so that we can get the focus that we want. Inside one instrument, we have a little grid that will block out the light of an individual star. It's a 2,000 by 2,000 array that can block out the light of an individual star so that we can do coronography in a telescope like that. And it's operating, like I said, at 30 to 40 Kelvin, depending on the instrument. So we have all these mechanical elements that are working there. So today, with this telescope, we have already changed the way we do a lot of things. Bonding at low temperature, that's something that JWST has delivered to us. Metrology, we can't test this like we test all of our other spacecraft, so we have to test it in pieces. This segment will be tested at JSC, the Johnson Space Center, because it's too big to test at Goddard. Behind it is an instrument segment. It will be tested at Goddard, we'll put the two of those together and test that at the Johnson Space Center. The individual layers can't be tested in the vacuum chamber, so we have to test subscale ones, compare our models to what we see in a 1G environment. And down in Huntsville, Alabama, we're testing those upside down and upside right, so that we can take into account gravity effects, correlate that to our 1/3 scale models of what's there. The metrology that we have to do here, we're talking about 20 nanometers difference in the location of the test equipment with relation to the telescope equipment. That's what we need to do in order to make sure we can do the error budget. All of this has already started to play into it. How many mechanical engineers are in here? You all know what shell buckling is? Kinda? Okay, shell buckling, all of our knowledge on shell buckling started in the 1960s with the Apollo program and also some of the other defense programs that were going on. So there's a bunch of knockdown factors that have been there since the 1960s. And in two unrelated things, and I have to give credit to my friends at the Langley Research Center and Marshall Space Flight Center for doing this, the metrology, the improved metrology capabilities developed by JWST have allowed us to measure much better the shape of materials. At the same time, we have much better computers. And one of the things that they were able to determine is with better measurement of the shape, better computers, we can improve our shell buckling calculations. And as a result, we can get increased capability. So for instance, on the SLS, the next generation rocket, they believe they can increase the performance by several percent to perhaps several tens of percent, because they can reduce the amount of material they have to carry, therefore you can lift more. So there's an obvious application to space. But think about aircraft. Aircraft, if you know, I'm not a mechanical engineer, although I obviously pay attention to a lot of it. Your cars, your airplanes, our trains, anything that has a shell or something that can be considered a shell can now be lighter or carry more or do more as a result of that. So that's an example of what you get with an interdisciplinary capability, what our engineers and scientists working together with industry get. The person sitting here is John Mather. He's our Nobel Prize winner. He's been at Goddard all of his career. He does science research, but he also does something that any scientists in the room or people studying science, that is something that we're really proud of at Goddard Space Flight Center. For every one of our missions, almost every one of our missions, we have a project scientist, somebody that understands the science well enough to work with the community. John was the project scientist on Kobe. He was also one of the inventors of the technique to be used with his colleague at Berkeley, George Smoot, that developed the whole idea of looking at the cosmic background radiation from space and developing instruments that can do that. And he is now the project scientist on the James Webb Space Telescope. So he got to do his research as well as help guide groundbreaking missions like Kobe and what we hope the James Webb Space Telescope is. We have another mission that I'll mention that's coming up in the future. It's the magnetic multi-scale mission. And this is, again, to look more at the interactions of the Earth's electric field. It's going to fly 4 spacecraft that spin. And as you can see, they have a number of appendages that stick out. So again, for those mechanical engineers out there, we got to figure out what the spin rate is to keep those wires, and they really are wires, taut and able to do the measurements that need to be done. And I'm breezing through some of these because in the interest of time. JPSS. I mentioned earlier that Goddard and NASA were there at the very beginning of space observations of weather with the first weather satellite in 1961. Since that time, every geosynchronous satellite, every polar satellite that measures the weather for civilian applications, and actually for other applications as well, has been developed in concert with industry and Goddard and other NASA centers. JPSS is a copy, I showed you that blue marble earlier, of a mission that we actually developed working with our colleagues in the Department of Defense and NOAA to do research and risk reduction. Due to difficulties with another mission, it ended up having to become an operational mission. It wasn't what it was originally intended to do. In fact, the name tells you everything. It was originally NPP, the NPOS Preparatory Project, something to go off and do an experiment. Well, now it's an operational satellite orbiting the Earth. It's doing so well that it's been decided that will become an operational, it'll be the model for operational satellites. So this is a mission that we'll be flying in the future, and there's lots and lots of work going on with that. Let's see, why didn't it change? There we go. Talk a little bit about the other part of what Goddard does. One of the things that Goddard's very proud of is we've been involved with the human spaceflight program since its inception. Every communication, every heartbeat, every bit that's ever come from a human mission up to today from the ISS has flowed through equipment either at Goddard or developed by Goddard. Today, most of those bits come through the tracking and data relay satellite system. Again, working with industry, we're going to launch, hopefully, early next year, TDRS-K. It's ready to ship to the launch site. We're just waiting for the rocket to get cleared, and it'll be flying. This is just a continuation of what we've done. So that gives you sort of a flavor of what we do at Goddard and all of the opportunities that are there. But communications today is changing. Many of you know, any electrical engineers in the group here? No? I'm unique today? Okay. Oh, there's one. All right. You know that that bandwidth is becoming limited as more and more people are using it for terrestrial communications. So, and also people want to communicate more and more information. So we need to find different wavelengths to exist in. So we're developing two systems to demonstrate improved capabilities and to get us away from the RF spectrum. And that's one of those experiments is going to fly on LADI, which is a mission that's going to the moon. It's being developed by the Ames Research Center. And working with our colleagues at Lincoln Labs, we're developing a laser communication system to demonstrate that at least from distances beyond geosynchronous orbit, we can communicate with lasers direct to Earth. So it's not going through a relay in orbit, it's going direct to Earth. And we have a couple of sites on Earth that we've decided that we're going to go off and use. And then we have a mobile device so that we can move it around and try and determine the best site to downlink data from. At the same time, we're working with industry, and I mentioned before that we do a lot with industry. So in this case, we're working with L'Oreal to put a laser communications device on one of their communication satellites, and you can see the synergy. If they can downlink that, and with a laser communication all by itself moving to that wavelength, you can get 1 or 2 orders of magnitude greater data rates than you can with RF communications. It's just a matter of dealing with to make sure that we have the downlink sites in the right places. And as it turns out, we put our RF downlink sites in places that are relatively cloud-free as well. So it's an area that we're working on to improve. I want to talk a little bit about something else to give you an idea of what young people can do, new engineers, new scientists coming out. In the 1970s, when we knew the shuttle was going to fly, we had an individual at the Goddard Space Flight Center named Frank Ceppolina. He's still there. I'll show you a picture of him later. He's not young anymore. He had an idea that if we're going to build this shuttle, we ought to take advantage of the capability of having humans in space, and that would allow us to do servicing of satellites, maybe repurposing of satellites. And not many people thought that this was a very viable thing. In fact, how many of you know about the Hubble Space Telescope? Okay, so you know it was serviced in space by astronauts. But the original concept was the shuttle would drop it off, and every few years, and I don't know what the every few years were, it would go up there, fold it all up, bring it back to Earth, and we'd service it on the ground. It wasn't intended to be serviced in orbit. So Frank had this idea that we should build missions using modular spacecraft, which we did do because there was cost benefits associated with that, and that we should go up and service them. So in one of the early shuttle missions, they went up there to a mission that had completed its life, and as an experiment, they went up and they revived it. The mission happened to be the Solar Max mission, but that's not really the important part of it, because it had completed its mission. So astronauts went up there, they birthed it, and in what ended up being a preliminary to the Hubble servicing missions, they replaced some components, put new components in place, and restored the spacecraft operation. That gave people the confidence that not only could we do the Hubble servicing mission now in space, it saved Hubble, when you think about it, because we launched it with a spherical aberration. And as a result, we were able to, there we go. We were able to save the Hubble mission. And then Hubble demonstrated with the complexity of the servicing that in fact you could build a space station. Prior to that time you wanted to put the pieces together, and now you're doing complex tasks. You're removing instruments, you're installing instruments, you're removing solar arrays. Things that are not easy to do on the ground, we're able to do in space with people in big bulky suits. They have a hard time moving their fingers. Dexterity is different, your ability to feel is different, sitting at the end of a robotic arm. So it really changed our understanding of it. Why am I mentioning all of this? Because we haven't stopped. One of the things that's going on now, I hope, no? Yes, well, sort of. By the way, that's Frank today. But 40 years ago, he didn't look like that. He is now taking us to a new stage. I had mentioned, I mentioned earlier how our robotic explorers did some limited experiments, prior to astronauts landing on the moon, and now they're working together. Well, the next step is to go off and use those robotic missions to do the servicing that we did with humans before. So on the space station today, we have an experiment where with supervised autonomy, people on the ground, not the astronauts on orbit, they have gone off and cut lock wires and removed washers and put washers on. All sounds rather pedestrian, but this is being done, from the surface of the Earth while something's orbiting 200 miles above us. Later this month, we're going to demonstrate that we can take a tube and transfer fluid, all doing it robotically. Now you might say, why is this important? Well, as we want to go off and do things further and further away from Earth, you want to have a robotic sentinel that can maybe prepare the way for you, whether it's on the surface of Mars, the surface of the moon, at a libration point, or a geosynchronous orbit. We're also working commercial areas. This is an example at Wallops where we have stacked now the first stage of the Antares rocket. It's a commercial rocket. It's a new venture that we're experimenting with in NASA. The pad is, which I don't know if I'm pointing to the right thing, I think that's right about there, was developed by the state of Virginia with help from NASA. The rocket is developed by Orbital Sciences Corporation with colleagues in the Ukraine who have developed the engines. And the purpose of this, initially at least, is to go off and help resupply the space station. Many of you are aware of SpaceX's recent accomplishments in servicing the space station. But we really need two vehicles in order to carry up all that we need to the space station. Now, part of the reason I was asked to come here was to talk about our future. I hope I gave you a bit of a sense of it. We've done some great things in the past. For the scientists among you, that data is still available and will be available. There's new things to be pulled out of it, like the Hubble Deep Field that took images that were taken 20 years ago with images that were taken today and everything in between, and they were able to do new science. The Landsat, same thing. Data taken 40 years ago compared to today is doing new science. But we're also doing new missions, like understanding the sun, so that we can get our astronauts more safely away from the planet Earth, coming up with new communications technologies that are needed there. So, what's out there? Why should you care? Goddard employs about 10,000 people. About 3,000 of them are civil servants. About 6,000 of them are contractors. And we work very closely together. That's just local to our facilities. It's a much larger number when you look outside. And when you look at NASA, it's about the same. We hire about, in the civil service side, we hire about 100 people per year. Sometimes more, sometimes less, but on average about 100. The contractor side is probably closer to 300 or 400 that are local there. And it's all really neat stuff. And we need everybody from business majors to engineers to scientists to go off and work on it. For those that are still undergraduates, we have a co-op program where we bring in every summer somewhere between 300 and 500 students to participate in our experiments. We get many repeat experiments. I know we have a couple of co-ops that were at Goddard this year, and there were a few from UB this year as well. I liked that because I got to find out how the Bills were really doing. I didn't really like that. I'd like to know how the Sabres are doing, but no one will know that. So, so there's many opportunities out there for you to participate and do some great things. And you're right, we're at a crossroads. We're at a crossroads again, like we were in the 60s when we started to go to commercial launches. People don't realize that our satellites are not launched on government-developed vehicles. They're launched on commercial vehicles. Communications, for the most part, was turned over in the early 1960s to industry. Now we're starting to realize that near-Earth orbit for humans is something where we start turning that over to industry. So that's one crossroads. The man-machine interface has become a very different thing. When you can put capabilities that didn't exist 40 years ago on Earth, on another planet, you've changed our ability to interact with our environment. When you can build telescopes 6 meters in diameter or more, you've changed things. So we're in a real shift from where we were before. And those of you who are in college today or just recently graduating, you're going to help us take that crossroads and either go off and expand and do better and better things, which I'm sure we will do, or do them in different ways, which I'm sure we'll do as well. And it'll be up to you to choose the path you want. And our motto at Goddard is something that Robert Goddard said almost a century ago, and I don't think we can, and I don't think I can end on a better note than his notes, if I can find them. It's difficult to say what is impossible, for the dream of yesterday is the hope of today and the reality of tomorrow. So I'm doing the hope, you'll do the reality. So thank you, and I don't know if you want any questions or anything. Why don't we do a few questions if there's time? Anybody? Yes. Oops.
How was your time in
Well, I think I broke the microphone. So that wasn't a good thing. But I think UB was great. It gave me a real background in a cross-disciplinary way. When okay, is this better? Yeah. One of the things that UB gave me that I don't see at many universities is really a cross-disciplinary education. When I think about it and I look at some of my colleagues, again, I mentioned I'm an electrical engineer. I took thermodynamics, I took industrial engineering, statistics, lots of math, and it's been invaluable because one of the things that you find when you get out into the workplace is you don't have to be an expert in it all, but you sort of have to know it all. And UB really gave me that opportunity, and I appreciate it. Any other questions? Nope? Okay, thank you very much.
We're going to start first with somebody who's particularly special to us. Mr. Scolese is a graduate of Buffalo, or UB, and he currently serves as the director of Goddard Space Flight Center. He previously served as acting NASA administrator in 2009, and he is current head of one of our nation's most critical robotic research facilities. So we welcome Mr. Scolese.
Well, good morning, everybody. I see we're starting kind of early, so we're going to have to filter some people in. How many students are here, since I see a number of ties? Okay, so students are just probably rolling out of bed anyway. Well, thanks for inviting me here. It's great to be back in Buffalo. As was mentioned, I grew up here, not very far from downtown Buffalo. We have another Buffalo native as well here. We'll be talking to you today. To let you know, I graduated from the University of Buffalo in 1978, and started my career in the Navy, and eventually ended up at NASA, where I really always wanted to be, doing some great things as you heard about. But just to let you know, for any of you who are from the University of Buffalo, we have 12 other graduates of the University of Buffalo at Goddard, and we have several at the within NASA. So let me get started and start talking about Goddard. Let's see. SEDS prize. John Mather is at Goddard Space Flight Center, and they got it for a satellite that was actually built at the Goddard Space Flight Center called the Cosmic Background Explorer, or COBE. Hubble has supported at least 2 Nobel Prizes with the results from Hubble, most recently in 2011. And we continue to move on with science missions with WMAP, getting a distinguished award. Oops, that's going the wrong way. There we go. This gives you the sense of some of the 300 missions that we did, and what you can see with all the missions, and they're sort of organized by where they are. There's several around the Earth. They're looking at the Earth or looking out at the cosmos. There's some around the sun or focused on the sun, and there's several that have gone to the planets. Although in the case of the planets, I have to say that that what Goddard does is mostly build the instruments that go to the planets. And as of today, Goddard Space Flight Center has built more of the instruments that have flown to the planets than any other organization in the world. We fly on JPL spacecraft, we fly on international spacecrafts from ESA and Japan and other nations. We do have a few planetary missions or interplanetary missions that we do. I'll talk about two of those coming up in a little bit. Now, one thing I do have to sit down and talk with Jack Schmidt, who was on Apollo 17, and he gave a splendid lecture that if you ever get a chance to hear it, you should really go and hear it, particularly if you're a geologist. I'm an electrical engineer, so I appreciated it, but I probably couldn't appreciate it as well as a geologist. And what he did was Apollo 17, Taurus Littrow, 40 years later. And you might say, well, gee whiz, he didn't go back there. Obviously, no one's gone back there since Apollo 17. But with the data from LRO, he was able to do a walkthrough of where they went on the moon during Apollo 17, what they learned while they were there from the rocks they brought back, and how the data now that we can get remotely from our spacecraft has changed their understanding or confirmed their understanding of what they learned about the moon from Apollo 17 and actually all of the Apollo missions. So it was just a spectacular lecture. I think it was videotaped. I think you can probably find it on YouTube at some point. And it was about an hour, and it's well worth listening to if you want to hear stories about what it was like to live and work on the moon, but more importantly, what we learned and what we're continuing to learn. I don't want to do that again. There we go. We also are looking at the sun, as I mentioned earlier. It's the nearest star to the Earth. Obviously, it's life-sustaining for us, but it's also creating nuisances as... did it change up there? No. Let's try again. Doesn't seem to be working. There we go. Okay. Talk a little bit about Goddard. It was the first center started by NASA. Now, many of you who know the history of the space program know that there was a JPL before there was a Goddard, and there was a Marshall before there was a Goddard. But those were under different organizations, and there was a Langley before there was a Goddard. It was NACA. But after they formed NASA, they started with, my screen up here keeps on flickering, which has me a little bit confused. Sorry about that. They created Goddard Space Flight Center in 1959. And the purpose of Goddard is really to go off and do the exploration of the universe and our Earth. We have the largest collection of scientists and engineers in the U.S. In the old days, it used to be Bell Labs, but with Bell Labs going away, we took the #1 spot. We've had about 300 successful missions throughout the life of the Goddard Space Flight Center. And we continue to do more and more missions. Some of the highlights of our missions is we did the first weather satellite, and we continue to do weather satellites. The Hubble Space Telescope, mostly the repair missions and that went on, and many more. We have the 2006 Nobel Prize in Physics. One of the people that should point out is we don't consider the moon another planet, so we've had many missions going to the moon as well. Oops, okay. As you can see, the missions span everything that you would think for a science center. We do the astrophysics, as I mentioned, that's looking at our, the fundamental structure and fabric of the universe, to understand our place in it. Heliophysics, to understand the sun and its interaction with the Earth. Planetary and lunar, to understand our nearest neighbors. Earth science, to understand our Earth, and I'll talk more about each of these. Cross-cutting technologies, communications, and the suborbital programs. I'll spend a bit of time on those. I mentioned the moon, and we have a satellite LRO that was built at the Goddard Space Flight Center, launched several years ago. It's orbiting the moon. It has some interesting instruments. This is showing the topography of the moon. It's a laser instrument that was developed, designed, and built at Goddard Space Flight Center. And combining it with imagery, we're able to get the relief of the moon and provide us much better indications of where to land when we send humans or robotic spacecraft to the moon. It also proved without a doubt that we landed on the moon. So those people that say we didn't, there's the Apollo 17 landing site. And you can see some interesting things. You can see the lander, you can see the rover, but more importantly, you can see the tracks that are there. I had the opportunity to